Hello, this is Chapter 7 on precipitation processes, and we are going to basically assume you can now access your PowerPoint slides under the correct section in the course. For this Chapter 7 is under Unit 2, under Chapter 7. You should be able to locate it there. I'm going to go ahead and start the presentation, which is uh, much shorter presentation than Chapter 6. And the presentation is on precipitation processes. What does it take for a cloud to produce rain? Just because you have a cloud or condensation in the upper atmosphere does not mean you get precipitation. This chapter deals with what has to happen within a cloud for cloud droplets to become precipitation or rain droplets. So clearly, not all clouds do precipitate. Precipitation requires dramatic cloud droplet growth. In fact, we need for cloud droplets to grow by a factor of over 1,000,000 times. The reality is that cloud droplets are lighter than the air holding them up. So what we realize is that most clouds do not produce precipitation because most cloud droplets never reach a heavy enough weight for them to become heavier than the air, keeping them afloat. And when they do, we call that the terminal velocity. And that is when cloud droplets become heavy enough that gravity will pull them down through the air against the resistance of friction holding them up. So when we look at cloud droplets versus a cloud droplet versus a large cloud droplet and eventually a precipitation or a rain droplet, they are much, much smaller, and it takes cloud droplets to grow many, many, many times over. And simply put, very few clouds have enough moisture within them to allow cloud droplets to become large enough to fall. And that's why we see only 2 clouds have the word nimbus in them, because most clouds do not have enough moisture in those clouds to allow cloud droplets to coalesce together to become rain droplets. So we need, for clouds to grow, we need cloud droplets to have some sort of condensation surface for them to form on. And we talk about condensation nuclei in the atmosphere like salt or dust or volcanic ash or dirt from a farm field. And generally speaking, most cloud droplets condense off of condensation nuclei, and these initial cloud droplets are very small, less than 20 micrometer. And these cloud droplets with that small of a radius simply are just too light to fall as precipitation. So what we need for cloud droplets to coalesce around each other to become larger. And when they do, we have 2 different processes that we have mapped out that basically talk about the evolution of how cloud droplets become precipitation or other forms of precipitation like snow or hail or freezing rain that indicate that cloud droplets have coalesced to become large enough to fall down through the resistance of friction. One process is called growth through warm clouds. And this is called the coalescence process. And the process looks somewhat like this, where we have a larger cloud droplet called a collector drop that through the force of gravity becomes heavy enough that it begins to fall down through a cloud. And as it falls down through a cloud, if it interacts and absorbs upwards of 1,000,000 smaller cloud droplets around it, it will reach a critical enough weight that the collector drop will reach a large enough size for it to fall. The key factor that distinguishes warm cloud precipitation is that it is forming in clouds where the water is above freezing. So in these clouds, probably closer to the equator, these clouds are basically formed of water all in the liquid phase. Whereas when we go into the mid-latitudes and towards the polar regions, we start to realize that we have water forming in environments in which water is beginning to freeze. And that's where we begin to talk about cold cloud precipitation, or the Bergeron process. And in this process, or the cold cloud precipitation as another way of saying it, we actually see that most precipitation actually starts out in clouds where water is actually existing in all 3 forms. And I'm going to kind of go to the picture first of water existing in vapor, Then we actually have cloud droplets, and then we have ice crystals, or early what we would call snow. And over time, we begin to actually see that the pull of the ice crystals, water in the solid form, begins to have a stronger pull of the existing water in the cloud. And most of the aggregation or deposition of water is occurring and being pulled towards water in the solid form in the colder regions of the cloud. And as a result, the ice crystals begin to grow over time much faster than the cloud droplets in the liquid phase. And that's why in the Bergeron process, precipitation often starts out much of the year first in the form of snow. And then as the snow begins to descend into warmer areas, it melts upon descent. So this is a fascinating example of how precipitation throughout much of the year occurs in the mid-latitudes and polar regions. It leaves the cloud in the form of snow and then melts as it moves into warmer air as it descends closer to the ground, and usually melts most of the year. But during the winter months, obviously, we know that the precipitation can stay in its frozen state. So this is what a cold cloud or Bergeron process environment looks like, the classic cumulonimbus cloud, where we see ice crystals existing in the higher levels in the cloud, and as water vapor funnels up into the cloud, those water vapor molecules are going to be attracted to the ice crystals faster, and as a result, the ice crystals will begin to descend down through the cloud, and ultimately they will reach a critical enough weight that they will have enough weight that they will reach terminal velocity and begin to fall down to the ground, and often will melt upon descent as they begin to move into warmer regions of the atmosphere as they get closer to the ground. That is not always the case, though, in the mid-latitudes, as often under the clouds in winter, the air is still below freezing and it falls exactly the way it left in the form of snow. So we know that in the mid-latitudes where we live, that we could see snow occurring in all, or we could see precipitation occurring in all variety of forms, from rain to snow to hail to sleet to freezing rain. And one of the keys is, what are the environments look like that produces snow, freezing rain, and hail? All is based upon the temperature within the cloud and under a cloud, and that determines what type of precipitation we might be getting. When we're talking about snow, just looking at annual snowfall amounts and inches of snow a year, we can clearly see the effect of just the annual distributions of snowfall. Are obviously, there's a magic line over the middle of the country that we can see where the highest levels of snowfall amounts occur, often on the slopes of mountains with the Rockies. And then at some point you could see you reach far enough south that it becomes warm enough that certain places far enough south, the air is always above freezing below the clouds, and ultimately the snow is melting and ultimately is falling in liquid form. So that's why you can literally see some of the rain shadow effect along the mountains with heavy snowfall amounts out west, but also the effect of as you move further south as well, you could see snowfall amounts drop dramatically as we get into areas where we know the air is above freezing beneath the clouds and the snow is melting. Lake effect snow is not a process we're going to talk so much about where we live in the middle of the United States, but if we were living closer to the Great Lakes, like in cities like Buffalo or Chicago, we would spend more time talking about the effect of lake effect snows and how they could occur. And I'm going to skip over these slides. And the process of rain, and when we look at precipitation amounts over the globe, for that matter, it's fascinating to see a map like this, and we can begin to try to figure out, why are some places getting so much rain around the equator, and then you could see some of the drier places that are the deserts in North Africa, the Middle East, the Gobi Desert, eastern Russia, Australia. A map like this shows you just how dynamic precipitation patterns and inches of precipitation annually of how varied the Earth is in terms of how much rainfall does occur. One of the fascinating questions you should begin to ask is, what are the lifting mechanisms? Why are some places like the rainforest in Brazil so much wetter than, say, places like North Africa? What mechanisms would go into producing a desert versus a tropical rainforest in the middle of Brazil? I will expect as we move throughout later units that you will begin to really understand and make sense of a map like this, of trying not just to see a map and recognize where there's more and where there's less, like in the middle of Australia, more precipitation and less precipitation, but I would begin to have you understand, what are the lifting mechanisms? What's the humidity patterns? How are all these things tying together to produce this varied environment of total inches of precipitation? Here's a map of the United States on a more local level of trying to understand the eastern United States being much more reliably, in terms of the inches of rainfall, do not vary that much throughout the year, whereas out west we see a much more varied environment. The first thing you would probably want to recognize is why the west is so much more varied is the fact of the role of the lifting mechanism. Out west we have mountain ranges that are significantly affecting how air is lifted, on one side producing windward heavy rainfall, and on the leeward side producing very dry conditions. Without the presence of any major mountain ranges other than the Smokies, the humidity out east gets more evenly distributed, and that's why we see a much more even distribution of precipitation in the eastern United States. Whereas out west we can see a clustering on the west coast of the United States because of the presence of mountains. It's applications like this that really test your ability to understand why there are such varied precipitation levels over the United States and for the world for that matter, and understanding how our ancestors figured out where are viable agricultural areas, where there are less viable agriculture areas, and how do we deal with the challenges of those varied environments. When we talk about different types of precipitation like graupel, hail, and hail frequency, and sleet and freezing rain, there are a series of videos under Chapter 7 that really talk about the effect of what is the temperature within a cloud, what is the temperature under a cloud, and what is the temperature of the air near the ground. I would highly suggest you to look at those videos and really understand how complex the environments are underneath clouds and within clouds that determine, on days that we are going to get precipitation, why we get such varied types of precipitation, especially in the Midwest. With our very complicated weather, with our clouds forming potentially with water existing in all three states, in the liquid, in the vapor, and in the solid phase, and then we have temperatures are underneath clouds, sometimes above and below freezing. It should be no surprise that in the Midwest we have such varied conditions that allow us to see all types of precipitation, which are not necessarily the case. I would highly suggest you to watch the videos that talk about the different types of precipitation and the conditions under clouds relative to temperatures, and why sleet and freezing rain can occur here but potentially not near the equator. And obviously we have rain gauges and how they work. Not a lot of questions will be occurring on the test about measurement instruments like rain gauges, but however they are the backbone of how we measure rainfall and how we measure the varied conditions over the earth for which areas are getting more or less precipitation. And I'm going to speed through these slides here because there won't be a lot of test questions on them, but obviously new technologies like radar are revolutionizing our understanding and our abilities to actually visually see how heavy moisture content levels are within clouds and rainfall amounts, and our ability to use technologies like Doppler radar are transforming our ability to see how heavy rainfall levels are within approaching storms. And obviously within this slide here you can see red areas and dark brown areas are areas with heavier rainfalls, and this is what allows us to understand and pinpoint exactly where storm cells are, and these technologies are the backbone of our modern severe storm forecasting. Understanding snow amount, snow equivalents with precipitation, and since snow is primarily so much of it is made of air. It takes 10 inches of snow to equal 1 inch of liquid precipitation. And we have our understanding of understanding how precipitation processes has gotten so dynamic. There is little case studies of how cloud seeding is a works, and I would actually suggest for any of students to watch this. Not that there'll be a lot of questions on any quizzes or tests, but understanding how cloud seeding works and the fact that humans can actually initiate clouds to produce precipitation when in fact often they might not have produced precipitation is the beginning of human altered weather. And understanding cloud seeding, there's some classic and fascinating YouTube videos, and if you were to YouTube the term cloud seeding, you could watch some classic videos of how it works, and it would be a good review to understanding exactly how the Bergeron process works exactly to produce deposition on ice, and how scientists are now actually initiating precipitation events in clouds that normally wouldn't be able to produce precipitation. That is the end of Chapter 7. Chapter 7 is a chapter that we often do not have a quiz on. Again, the themes of Chapter 7 primarily relate to our focus on just understanding how do cloud droplets grow and become precipitation, and once precipitation does occur, what are the environments under clouds that often produce the different types of precipitation in terms of how temperature within clouds and under clouds affects what types of precipitations we may or may not be getting on any given day.